So as we move further into section 5.5, let's look at a word problem involving the graph see if we can make a binomial probability turn into a normal approximation. So in a survey of 8 to 18-year-old heavy media users in the United States, 47% said they get fair to poor grades, C and below. You randomly select 45 8 to 18-year-old heavy media users in the United States and ask them whether they get fair or poor grades. So what's the probability that fewer than 20 of them respond yes? So our goal, first off, is to see if we can make this binomial distribution, see if we're allowed to actually use the normal. So remember, we have to pass two tests. So doing this, we know that n times p has got to be greater or equal to 5, and n times q must be greater or equal to 5. So we selected 45. So let's multiply 45 times the probability, which would be 47%. So they said that they actually do get poor grades. So if I use my calculator, I don't know if that's considered a success, but yeah, it's technically a success based on the responses. So let's see here. So 0.47 times 45, that's going to give me this 21.15. So that's okay. And then if I go 100 minus 0.47, that gives me the failures, if you will. So that's going to be, oops, so I should use 1 instead. 1 minus 0.47, because we're in decimal form. So 100% is actually 1. That gives me 0.53. So if I multiply 0.53 times 45, we have to get greater than 5 again. And we do, we get this 23.85. So both of these, we pick up on that. Like I said, this would be 45 times 0.53. And both these were greater than or equal to 5. So that means we are allowed to use a normal approximation. So as we move into the problem, we know we have to know the mean as well. So the mean, they actually did that for us in the graph. It's 21.15. But also, it was, n times p was the mean, which we got 21.15 there on the calculator, I believe. So yeah, 0.47 times 45 was 21.14, 21.15. So that's been done for us. Now to do the standard deviation, we need to know the square root of, so it was n times p times q. So it's going to be the square root of 45 times 0.47 times 0.53. So it's going to give us our standard deviation. So I'm going to have to slide that over. I can't remember all those numbers. And then I'm going to pull up my calculator. And we'll clear this all off. So the square root of 45 times 0.47 times 0.53. And that gives us then this 3.34. So we'll say 3.35 would be our standard deviation. Excuse me. So let's pull this back up for a second. We're still going to need our calculator. So now we need to pick up on our graph here. So it says fewer than 20. So remember, if I draw my number line, here's 20, but fewer than 20 means left of 20. And we don't include the 20 either. So since we don't include the 20, when we do our continuity correction, we have to actually subtract a 0.5 from the 20. So that would give us actually this 19.5. So if you notice in our graph, it's actually got this 19.5 and to the left. So if I'm doing the probability, my probability becomes then X is going to have to be less than 19.5. So using our calculator, I'm going to need all that information that we have here. I should be able to find the normal distribution as a replacement for the binomial. So if I hit second distribution and use the normal one, number 2, the lower bound, notice that there is no lower bound because it goes to infinity. So we've been using a big negative number. So it's going to be like a negative 10,000. And then the upper bound, we can't go past 19.5. And then our mean was the 21.15. And our standard deviation was 3.35. So this allows us to avoid the tables and all the z-scores by doing it this way. So if I hit enter, it'll paste it in for us. Hit enter again. So we end up with then, I think they usually do this to like 4 decimal places. So like 0.311. So that fourth one there, since there's a 6 there, 0.311. That third one actually has to turn into a 2. So 0.3112 would be our probability. So around 31%, 31.12% if you want to be all the way across there. So that'd be our probability. So we were able to take advantage of the normal approximation to do that problem. But notice how we had to do that continuity correction to do that. So let's look at another example. So a study on an aggressive driving found that 47% of the drivers say they have yelled at another driver. You randomly select 200 drivers in the United States and ask them whether or not they have yelled at another driver. What is probably that at least 100 drivers will say yes, they have yelled at another driver. So what they're saying about 50% there. Interesting. It's probably a good chance of that actually, at least one time. So again, to see if we can actually use the normal approximation, we got to check n times p and see if it's greater than or equal to 5. So we're selecting 200 people, and the probability that's going to be like 0.47. So if we do that math, let's see here. Where did it go? So I have 200 times 0.47. That's going to give me 94. So that's my mean is 94 actually. So that's definitely greater than. And then if we do 200 times 0.53, that's going to be n times q is greater than or equal to 5. So 200 times 0.53 would be n times q. That's going to be 106. So both of those are clearly greater than or equal to 5. So it's 106 there. Yeah, it makes 200. All right, so what's the probability at least 100 drivers will say yes? So based on our normal approximation, again, I'm just going to draw a number line here as an easier way to do this because we need to do that correction of continuity. And I'm going to put 100 up here. And it says at least 100 drivers. So what that means is 100 or more. So this is kind of what we're looking at. So if we're going to include the 100, we actually got to go left of the 100. So we have to subtract that 0.5 from that, and we're going to get this 99.5. So if you look up there, you can't really see that. That's kind of where this mark is. There it is right there, 99.5. So that's our correction. So this is going to be our normal distribution now that we can use. Instead of, like I said, the binomial distribution is more of a histogram. So this is more of a continuous curve. So basically what we're doing then is the probability that X is greater than 99.5. So that's what we're looking for. But to do that, not only do we need to know that, but we need to know the mean, which was the 94. And you can also see it up there. The mean was 94. But to do the standard deviation, we still need to do the square root of the 200 times the 0.47 times the 0.53 to get our standard deviation. So I'm going to have to slide this over again and use my calculator. So we'll clear this off. Second square root of 200 times 0.47 times 0.53. That gives us 7.05, which would actually be 7.06. So 7.06 would be our standard deviation. So we now can apply this to our normal distribution formula in our calculator. So I hit second distribution, and number 2 is the normal cumulative distribution function. Notice now our lower bound is actually the 99.5. That's actually where our interval begins. So I need that 99.5, and it goes towards infinity, which we use a really, really large positive number, which we're again just going to use 10,000. That's what the book kind of suggests. And then our mean now was 94. And our standard deviation was this 7.06. Therefore, our probability then becomes then this 0.2179, which actually is going to turn to an 80, because that 9's got a 7 after it, and that 7 is going to tell me around that 9 on up, so that 79 has to round to an 80. So that would be our probability, around 21%. Well, I thought it'd be more than that, but oh, well, I guess there's a lot nicer people out there than I thought. And that's kind of what looks like, it does look like a big percentage is shaded there, so 21% looks about right from the graph as well. All right, let's see what our next question is here. Sorry about that. So a study of the National Football League retirees ages 50 and older found that 62.4% have arthritis. And when you randomly select 75 NFL retirees who are at least 50 years old and ask them whether they have arthritis, what is the probability that exactly 48 will say yes? So on this one, again, they want us to use the approximation for this. So again, we have to kind of verify the NQ. Is it the NP? Is NP greater than or equal to 5, and is NQ greater than or equal to 5? So we select 75, and they say 62.4. That's going to be 0.624%. So multiply 75 times 0.624. And that's going to give us 46.8. So that's greater than or equal to 5. So that passes the test. And then, well, I got to do the other one too. So what's 1 minus 0.64? This finds us the failures. That's going to be 0.376. And I'm going to multiply that by 75. And that's going to give us 28.2. That's going to be our failures, if you will. Still forgot what that was. Didn't take long. 28.2. So this would be 28.2. All right. So remember, when we're doing exactly one, so right now, if I do my number line, the 49 is here in the middle, but since it's exactly the 49, what we do is we go 1 unit we go 0.5 to the left, which is going to now be this 48.5, and we have to go 1 unit to the right, or 0.5 to the right, which would be 49.5. So our interval becomes then really this, to include the 49, our interval becomes 48.5 to 49.5. So our probability is actually going to be this 48.5 x, well, less than x, which is going to be less than 49.5 would be our normal distribution calculation. But notice we do have our mean here, the 46.8, and notice how it was given here, but we still need to do the standard deviation. So sigma is going to equal then the square root of n times p times q, which would be then the square root of n was 75. The 0.624 was the successes, times then, I guess I have to look up on my calculator what that other number was. It was at 0.376. So we're going to multiply by 0.376 as well. So if I bring that over, pull my calculator back up, we're going to be doing, and again, I'll clear that all off. So the square root of 75 times 0.624 times 0.376. That will give us our standard deviation, which will be like 4.19. So I can now go straight to the calculator and do my my normal distribution. So I hit the second button, distribution number 2. My lower bound now is actually the 48.5. My upper bound is the 49.5. And my mean was 46.8. And my standard deviation was 4.19. Hit enter, paste that, and we end up with 0.0828. So let's see here. So 0.0828. So just a little over 8% was exactly that. So again, we don't expect a high probability there because they're saying exactly 48. So the probability should be fairly low on it. That sounds reasonable for this problem here. Let's see what else we got here. All righty. So that kind of concludes some examples involving approximating the probabilities there.